So now we're going to use these relationships between parental dye types, non-parental dye types, and tetra types to sort of count the total numbers of crossovers that have occurred, say for example, between A and B. And the advantage here is that while in sort of what we would call random spore analysis, lots of the doubles you can't even see because they happen in this fashion, crossover, crossover, and you do not see those crossovers. You actually have view to some of the double crossovers in tetrad analysis. All right. What I'm going to show here is sort of an overview now of the relationships between the sort of numbers of crossovers and the different types of tetrads, and we're going to use those relationships to calculate a formula to estimate the genetic distance between these two different genes. And of course, genetic distance is measured in centimorgans, and centimorgans measures the number of crossovers that occur between two genes. All right. So what I have up here, up top, is a scenario in which there might be a single crossover. Okay. So you have this type of scenario, and in that particular case, what type of tetrad do you produce? Well, you produce a tetratype because you have the two parentals and then the recombinants within there, so we'll just call that a tetratype. All right. Now, let's consider all the different doubles that can happen. All right, so the one scenario that we talked about, in which is we call the two-strand double. All right, so that would occur in this particular way. All right, and what does that produce? Well, that basically undoes this recombination event, undoes this recombination event, and that will create a parental dye type. Okay. Now, if you have a four-strand double, okay, right here, right, what does that produce? Well, essentially all the sister chromatids are recombinant in that respect. So these are recombinant and these are recombinant, and that produces the non-parental dye type, which in the case of unlinked genes is way less common than the parental dye type. Which in the case of linked genes is way less common than parental dye type. So these are the scenarios for the doubles. I should be more clear about this. These are all double crossover scenarios. And then over here we have the two categories of three-strand doubles. Okay, so one of them which you sort of have these two, and then you engage this homolog, all right? And then you have a crossover here. Now this strand participates in the third strand double, so you have this scenario, all right? And both of these will produce tetratypes as well. So what tetrads allow us to do now is they allow us to sort of do some sort of basic algebra to count up the amount of crossovers that have occurred. Okay, so what we want to do is consider how do we count crossovers within these different tetrads. All right. Well, the first way that we can do is we can consider how many tetratypes have occurred, because the tetratypes indicate how many single crossovers that have occurred in there. All right. So you might say, for example, count up all the tetratypes, but notice something: these tetratypes include these three-strand doubles. So we want to be able to really figure out how many of the tetratypes actually are the result of a single crossover, right? Well, what's kind of convenient here is that because of the ratio of three-strand doubles to four-strand doubles, okay, there's actually a sort of a 2-to-1 ratio of tetratypes arising from this type relative to non-parental dye types. So we can sort of correct our number of tetratypes to exclude the three-strand doubles by this, okay? We can sort of count up all the number of tetratypes, right? And we can minus 2 times the number of non-parental dye types. And you can see how that will now basically lead to the number that is of the tetratypes that are in fact due to single crossovers. Now, since we're counting crossover frequency, we need to remember that in these scenarios, only half of those tetrads actually produce recombinant products. And so we can put a number here times half, which is sort of a measure of the correction for how many crossovers actually happen in these meioses. Right? And then we can add up another class, which is basically all of the doubles. All right, and so you can see here that doubles arise this way, this way, this way, and this way, right? And there's a unique class of doubles, the fourth-strand doubles, which produce non-parental die types. And you can basically estimate, because remember, there's also going to be a bunch of parental die types that are not recombinant, right? So what you can do is you can estimate the number of 2, 3, or 4-strand doubles by just simply multiplying the number of non-parental die types by 4. Okay, 4 times the number of non-parental die types. And we don't do that half thing because in all of these scenarios there's 2 crossovers for each one, so on average each of the sister chromatids will be involved in a crossover, so you don't need to do this half thing. This gives us basically the number of crossovers that have occurred between A and B all over the total number of tetrads that we count, and if we want to convert into centimorgans, multiply it by 100. And there you go.